published in the IEEE Antennas and Propagation Society magazine, because earlier it was known as newsletter, now it's known as magazine. So he mentioned a very nice sentence: in antennas, spectral expansions always leads to innovations. Obviously, this has happened over the past decade, and even it is happening for the previous decades also. Particularly in the past decade, which I was mentioning about the large number of frequencies which have come up for applications in various wireless communication systems, has led to a lot of spectral expansions and therefore a lot of innovations in the antenna technology. So you can see some highlights that we see some 100 years before, more than 100 years before the transmitters. The one which was installed in the Titanic ship, it's a T-type aerial. Two modern compact planar antenna systems, some examples of arrays, and radio telescopes. So there is a different and varied applications. It's making it very small, geometries which are not having particular guidelines. Wherever you find space, you have to put in the antenna, fit in the antenna, which is very stringently designed so far as the handset is concerned, because with all the circuitry, you don't find the space for the antenna. You can see that the antenna system, which is the yellow part, is having not a predefined geometry. So you have to etch the antenna wherever you find a space, such that it can work out for the different frequencies which you intend for the cellular system. So therefore, the radio antenna, precisely, it's a radio frequency antenna. On other frequency domains also there are transmitters and receivers. So for particularly the radio antenna, we can consider that it's a transition between the guided wave and the free space. So it's acting as an impedance match network between that of the free space and the transmission line. Regardless of different types of antennas, we can emphatically say that radiation will occur whenever there is an acceleration or deceleration of charges. Though it is the basic way we generally tend to introduce antenna systems to the prospective electronics engineer who has gone through a course in electromagnetics, and we try to explain the fact that how the radiation will take place when there is acceleration or deceleration. It will take place whenever this acceleration deceleration is brought in the structure, and you can do so by either bending it. So for wire antennas, you just saw that if you start bending a transmission line, you make it, you just try to bend it 90 degrees, you get a dipole. And for planar antennas, many of you are working on that. If you just X slots, you can start the modifying the geometry. You can. Any doubt? Anybody was, any query?
Presentation is not visible, sir.
Presentation not visible?
Yes, sir.
I hope the presentation is visible. You can just see the window. You can pin the video. You can pin the presentation. It is quite visible.
It is full screen, so
it is visible.
Okay, the coordinator can confirm. Dr. Roy? Dr. Roy is present? Okay, that's a, okay. Thank you. So, as I was telling that you can either add some slots, you can change the dimensions along the edges, and somehow try to bring some geometrical perturbations which allows the electron flow to be either slowed down, and again it is accelerated. So whenever this occurs, there is some radiation. Now, but it is not exactly how the radiation of antenna takes place. Though it is well analyzed, it is the starting point which you get into when you read any antenna textbook. Along with this, you should supplement your understanding with this paper by H.D. Sands, Electromagnetic Energy Around Hertzian Dipoles, where he precisely mentioned, it's a new, at least it was published in 2001, much later than all the textbooks that we have followed, like that of Krauss or Balanis, and it is followed by you people also. It's fine that when there is acceleration and deceleration of charges, energy will radiate, but the manifestation of the radiation is greatly influenced by the reactive energy which is present just in the vicinity of the radiating system. That reactive energy is very crucial. How it gets developed, that gets translated, and over the distance which we generally call as the far field, we generally see how it radiates. But not only the acceleration and deceleration charges, that which forms the reactive energy in the vicinity of the antenna, that is very, very critical in allowing the antenna to radiate properly. So I hope that you can go through this particular paper for more understanding of the mechanism of radiation. So therefore, that you can see that when there is a current, and that's a source either for any elemental current carrying wire. So obviously when it radiates into free space, there is no free charges, so the divergence D is 0, so therefore the electric fields form closed electric field lines. And we can just relate this, that if there is a source, there is an electric field. So you have the above relation, and you can then form that what you can solve this to get the nature of the electric field, and obviously use the Green's function. So we are not here to discuss how you get this, because this is the one of the views that you get very few students lasting in antenna classes because of too many jargons and too many mathematical insights. But keep in mind that whatever you are thinking, whatever you're trying to explain, you can do so with these equations. It's not that the equations you need to remember and do this and do a lot of calculations and get afraid of this, but it is only thing is that you are mathematically explaining the facts what we are discussing. And obviously if you take the distance r, so as you go in the vicinity, move from the vicinity of the antenna systems to the distance, which is the far field distance, there you can see the variations in the field, how it occurs with respect to r. Obviously, you have gone through electrostatic and magnetostatic principles. So how the electrostatic field vary for a dipole plus and minus Q system. So you can just remember that. In fact, the field near the dipole antenna varies in that way. And therefore, this initial thought is very important for us to understand the design and characterization of antenna systems. And these are indispensable when analyzing circuit with passive components. First is the impedance. All of us are interested in this quantity. Then resonance characteristics. What is the resonance frequency? How the resonance frequency is changing by changing the certain parameters, dimensional parameters of the subsystem, changing the width of the line for a microstrip. Does it change anything? It changes the impedance. It doesn't change the frequency. So this thought, this which you know from undergraduate classes. So obviously when you start designing an antenna system, obviously we won't try to change the width of a microstrip line to change the frequency. And another factor, which is quality factor, very important so far as analyzing resonant circuits. This tutorial intends to discuss these characteristics. We'll consider it lossless so far as analyzing from circuit viewpoint, but when we consider the antenna systems, the conductor losses are predominant. The dielectric losses are also present, so which you cannot neglect in certain analysis where characterizing the efficiency of the antenna systems. And obviously when we consider antenna, another parameter which comes along with the resonance characteristics is the radiation characteristics. So therefore I chose to name the tutorial as Revisiting Antenna Characteristics. So when we talk about impedance, talk about the resonance characteristics, that is its axis. It is basically a resonator, a piece of a transmission line. If I bend it, its length lambda by 2, I change the length a little bit, fine tune it, I bend it, I make it a good radiator. So naturally, the concepts, where from it came from. The distributed circuit concept is inherently embedded into the entire understanding of any RF and microwave circuits. It was Lord Kelvin, Williamson Thomson, who was credited to introduce the distributed circuit theory, concept of impedance in AC circuits, V by R. That term has a lot of significance when we increase the frequency because the reactance changes with frequency. So therefore, the antenna reactance also changes with frequency because it's also a piece of a resonator, it's a piece of a transmission line, which inherently you have used in such an application where your purpose is not as a guided media, rather you want the fields to escape, the fields to be radiated out. And then obviously you have those who have been fortunate enough to go through the book of Shelkunov, who has written a very renowned book on antenna. So he was also credited for expressing impedance in terms of resonance frequency. And obviously, for a lossless passive network, we try to implement the concepts of Foster's, Ronald Foster, and the introduction of the Foster's reactance theorem, which helps us in understanding the resonance characteristics more precisely. And extrapolation of this particular Foster's reactance theorem from distributed circuit theory to the resonator concepts was by W.R. McLean. So it's quite a considerable amount of time which has passed out that the fundamental systems have been, the preliminary foundations have been in depth. And we read it in different semesters, precisely because in the semester forms. But if you try to stitch the informations which we derive from third semester onwards, I hope that you would take up any challenge for new trends in antenna design, perhaps only keeping in mind that the fundamentals which were laid down some 150 years before, they truly are not missing in present design, but somehow we are forgetting it over the days. I'm not blaming anybody that you forget it, but new researchers are there mainly interested in a lot of good papers, because ours is generally driven by how many papers and their total points. So naturally, I would not blame that you would be thinking a lot and then start designing them. So in the young researchers, they are mainly interested in running after new designs and bringing more papers. That's fine, but make a slight halt in your fast routine and just look back. I hope you can find a large number of paths which will end up in good applications and also improve your analytical skills. So when you talk about impedance, resonance characteristics, then obviously the well-known relations which you have studied in the electromagnetics and revisited in the network analysis classes, which interestingly tries to find the potential difference. If you know the electric field and you can find, if you know the magnetic field, you can find what is the current. So you can find some interesting link between them. You can see the left hand side, it's shaded now. It's having the circuit parameters V and I. And in the right hand side, it's the electric field and the magnetic field. So these two relations which are so beautifully placed in the entire domain of a electronics and communication engineer or a radio physicist, that it helps us a lot in relating circuit parameters with field parameters. Therefore, you have so many softwares now, and in fact, those softwares which are mainly dealing on circuit parameters, they have started acquiring those companies who were mainly dealing with numerical techniques in electromagnetics to bring the entire computation domain, because now you cannot tell that I am only an electromagnetic engineer, means I am only into electromagnetic field analysis, I understand electric field and magnetic field, and that is beyond and end all, and beyond that I cannot look at it as a circuit viewpoint. It's not. And a pure circuit designer who looks everything from an RLC circuit point of view, you cannot tell that I have not gone through the field calculations because I am only interested with circuit parameters. Now, in certain aspects, in certain points, in certain design steps, you have to invoke circuit analysis, understand them, change your design or go ahead with your design. And finally, you have to also go for electromagnetic analysis to understand that how well you can improve it or how well it can function by getting a clear insight on the current distribution source. So everything put together gives you a complete control on the design of any structural modifications you are trying. So the V by I gives you the impedance, and another thing is that the impedance of the line. That is looking from the generator end, what should be the input impedance. Obviously, these relations are too handy. You have read it in transmission line classes. I'm just going to make a recap. You just see that input impedance is, you can know the gate impedance, you know the load impedance, you can find it out. So obviously when antenna is connected to a source with a feed line, so at a particular point you can find what is the input impedance, and that input impedance you can compute, and that is helpful to you because after computing this you have to split it up into real and imaginary part and see how it varies. And this is not the input impedance which you think that it's only for a given frequency. Now the antenna performance, like any other microcircuit performance, you generally do analyze it over a wide range of frequencies, not only at the exactly over each bandwidth or the pass band region, or if it is for a stop band characteristic for a stop band region. No. The pass band characteristics as well as the stop band characteristics, the band edges, everything is important to you because everything matters. Because you cannot allow the antenna to be interfered with certain other devices. You cannot allow the antenna to interfere with other electromagnetic systems. Then it will be a culprit. It will be under electromagnetic interference. It will create EMI, and you need to have an electromagnetic compatible circuit for that. So therefore, The input impedance, you need to analyze before you proceed with the further computations on the resonance characteristics. And from there you can find that where the reactive part becomes zero, that's the point of resonance. That's also known from your third semester network theory classes. And obviously when you make an equivalent circuit, from there also you can see that the antenna impedance, you can split it up into real and imaginary parts. The real part is again the antenna resistance and the radiation resistance. The loss resistance together is the antenna resistance. And similar equivalent circuit can be made for a receiving antenna system. Now, from circuit viewpoint, you can find the input impedance, you can compute it, that's fine. In certain analysis, you also want to know about how much energy is stored in the electric field and the magnetic field. It's as simple. If you know how to compute the electric field for a given radiating system, you can easily use standard relations to find what is the energy stored in the electric field and what is stored in the magnetic field. And in fact, with the age-old relationship E by H is eta, finding only the electric field in the far field is enough. So how much energy is stored in the electric field, and from there you know what is the wave impedance in free space, then you can find what is the energy stored in the magnetic field. And with this concept of energy stored, thereupon you can find what will be the input impedance or the input admittance. From the circuit analogy viewpoint also you can come up with the same results. Now, once you get into the input impedance, either from calculating the total energy stored in the electric field or the magnetic field, or you can directly make an equivalent circuit and find what is the input impedance. You get the reactive term and the reactive part, X and B, that is generally obtained either from Z or from Y. For a lossless passive network, the slope is always positive. That's the importance of Foster's reactance theorem. If it is positive, then it should pass through alternate poles and zeros. And you can easily calculate that what is the resonant frequency, and if at a certain point it behaves as a stop band characteristics, then what is the transmission zero and transmission poles. Precisely if you follow the short circuit and open circuit impedance, I hope you can release the fact. The plots are in the screen. For the input impedance of a short circuit, lambda by 4, it is a parallel resonant circuit. It's a transmission pole. Short circuit lambda by 2, it behaves as a series resonant, you get the transmission zero. So for a lambda by 2 short circuited line, if you want to make it as a stop band characteristics, then you should make it as an equivalent circuit, which is a series resonant circuit. Another important aspect, not only with this, if you want to find the resonance frequency from the input impedance characteristics, from the input impedance you find out, you equate to 0, you determine what is the transmission 0. You find out the input admittance, equate it to 0, you find out the transmission poles. So you can find the resonance frequency, whether it will be a transmission pole or the transmission zeros, you can easily find out by either analyzing its input impedance or the input admittance. Another important aspect of the distributed circuit theory is you can see that a short circuit, little less than the lambda by 4, it will behave as an inductor, And the same lambda by 4, if it's an open circuit, it behaves as a capacitor. So instead of using a inductor, so we generally don't have lumped element values here. What you do in many circuit designs, when you go for matching elements for input feed networks also, and you want to balance one capacitor or the capacitive reactance in the input impedance, you can put an inductor. That inductor can be a high impedance lambda by 4 line, which is short circuit. So from there you can get the inductance. You can see how much inductance is required. You can choose the length of the line because it is the inductance, and with that you can see how much is required. And it should be also high impedance line because the inductors are generally very narrow width line. So a narrow width in microstrip line means high impedance. So if you try to analyze a square patch resonator, see what is the resonance frequency. So if you know the input impedance or the input admittance, find what is the resonance frequency. Either weakly coupling or you can do some analytical relations, find what is the input impedance and the input admittance. After doing that, you can use this square patch resonator either as a crossover, or you can same square patch resonator can be used as an antenna. So what I want to mean from here, that whether you want to design an antenna, it actually translates down into designing a good resonator, a good resonant element. Either in some cases, those I found that in this particular workshop there are other lectures also on very interesting topics like metasurfaces and MIMO systems and others. So where these kind of interesting small compact antenna systems are required. So it is quite small compared to the wavelength. There also there are sub wavelength resonators. So there you can characterize them. What is the resonance frequency? You can see whether it will create a stop band characteristics or a pass band characteristics, and you can use it for your applications to enhance the bandwidth. You can put it now. That analysis is not clear to you. I hope it will be a kind of a blind process where you just change the design day and night and then try to get something which is as per the specs. So you start with the spec, you divide the design into a very fundamental design, see what is the ingredients in this, what kind of resonators, what is the application domain, whether it will fit in that particular domain. And then when you analyze that particular circuit separately, it gives you a clear insight that what if I put this particular resonant element in vicinity of another element, or whether it will create a problem or it will add to its benefit. That's very important, and that helps a lot. So the characterizations, you can very well see that one based on circuit parameters, another is field parameters. So therefore antenna characteristics is also divided into circuit parameters and field parameters. The input impedance, radiation resistance, VSWR, return loss, reflection coefficient, radiation efficiency, impedance bandwidth, and from the field parameters,